Okay, so hello. For today we're going to be doing section 18.3, the first objective, because it's a pretty complex lesson, so I'm going to be breaking it down into two parts. For today we're going to be calculating equivalent resistance in complex circuits involving both series and parallel portions. So what a complex circuit is, it's a combination circuit of different smaller sub-circuits. So we're going to be finding today their equivalent resistance and either their total current or the potential difference across the battery or the EMF. Okay, so let's quickly review the formulas we were using. When you have two or more resistors that are in series, the equivalent resistance REQ is equal to the sum of all the individual resistors. On and on and on. Whenever you have circuits that are connected in parallel, you use a different formula to find your equivalent resistance. So it's 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3. You plugged all of that in your calculator and then you did 1 divided by the answer to find REQ. So today we're going to be doing these simultaneously in the same circuit. So why do we have to do that? So most of the time circuits, electrical circuits, are not only series and only parallel. In the prior examples I gave you the everyday example of Christmas lights. If you have one of those Christmas lights where if one of the light bulbs goes off and then all of them go off at the same time, you can't have some on and some off. That would be Christmas lights that are in series. And if you have a set of Christmas lights where one of them goes off or falls off and all of them remain on, would be in parallel. However, nowadays Christmas lights come set up so that, imagine you have 100 Christmas lights in a string. If one of them falls off, maybe a group of 10 lights next to that one are going to go off, but the remaining 90 are going to stay on. And the reason why that happens, it's because you're going to have smaller sub-circuits inside of the large 100 light circuit. And each of those sub-circuits is in series, but all of those 10 light circuits would be parallel to each other. So let's see how this works. In your homes, if you ever notice when the breaker goes off, when one breaker goes off, that's when remember we talked about that happens when there is a large surge of current to a specific area of your electrical circuits in your house. So the breaker will go off to protect from a short circuit. So when that happens in one of the systems in your houses, you're going to notice that maybe a corner of the kitchen went off. And this happens a lot when you're working, when you have the oven on and you have the microwave on, and maybe you turn on a blender and all that part of your house goes off. And the reason why is because that's the way they set up electrical circuits in our homes, in small subgroups. So let's analyze what one of those is. That's the example. Everybody, you have to have your book open to page 645. That's where we're going to start off today. You're going to have, here we go, down here. You have a microwave oven. That's a very old-fashioned looking microwave oven right there. You have a blender and you have a toaster, okay? And they're all on, and they're connected in parallel. So if you disconnect one of them, the remaining are going to stay on because they are in parallel. They're not in circuit. However, all of them together form a circuit with the circuit breaker, a series circuit. So if the breaker is a switch, if the breaker switch opens, that the circuit breaker is a switch that creates a resistance of 0.01 ohms. If this opens, then since this group up here together is in series with the breaker, it's also going to go off. So how do you work with this kind of circuit? You need to narrow it down. You need to start working, like when you're working in math and you have a lot of parentheses and grouping symbols, you work from the inside, first parentheses and grouping symbols, and then you work out. Pretty much it's going to be the same thing here. First, you need to identify smaller subcircuits, combine them, and then work your way out. So the way I do it is every time I combine 2 or more resistors into one, I redraw my new circuit so that it makes visual sense to you guys. And this is what I expect you to do in your assignments. Every time you combine some of them, draw a new simpler circuit with the equivalent resistance of the subcircuit you combine. So in order to do that, let me zoom in. I'm going to label these resistances, and I like using letters so you don't get confused with the numbers that are already there. We can call the microwave A, the blender B, the toaster C. The resistance of the circuit breaker is going to be D, okay? So if I notice right away, my inner circuit is up here where A, B, and C are all in parallel. So I can combine A, B, and C because I can clearly see that those 3 are parallel to each other. So my equivalent resistance of, I'm going to call REQ, RABC, because it's going to be the equivalent of combining A, B, and C. And since they're in parallel, I'm going to have to do 1 over the equivalent resistance of ABC equals 1 over 8.0 plus 1 over 41.1 plus 1 over 16.9. Okay, ohms for all of that. That's a 6 right there. Sorry about that. I already ordered my Apple Pencil, but it's taking a while to get here because I got it through Amazon. So that is 1 over RABC equals 1 divided by 8 plus 1 divided by 41.1 plus 1 divided by 16.9. And that's 0.2085. Round to the very end over here. 0.2085. And then to find RABC, it's going to be 1 divided by that answer, and that's 4.8. So the equivalent resistance of combining A, B, and C is 4.8 ohms. So since I already combined them, I'm going to redraw my circuit. So quick diagram. This shouldn't be hard for you to do. My battery. Instead of all of these, I am just going to put 1 labeled RABC equals 4.8 ohms. And then I have my circuit breaker over here, which is in the form of a switch, but it also has a resistance of 0.01 ohms. So once I combine those, you can notice now that I only have, and this is the way it always works, at the very end, you're only left with 1 loop. That's when you know you're done, when you only have 1 loop going around. And that loop can either have 1 resistance, 2 resistance, 3 resistance on. In this case, our loop has, so that's a 120 volt battery. I forgot to write that down. Our loop has 2 resistances, the combination of A, B, and C, and my D, which is 0.01. So those are obviously in 1 loop, so I can say that they're in series. So my equivalent resistance of A, B, C, and D, that's when I know I'm done. When my R has all of the letters involved in the circuit, is going to be, since it's series, just adding 4.8 plus 0.01, which is 4.81 ohms. And that's the equivalent resistance for the entire circuit. Since I now have REQ and I have my potential difference, I can now say that I can find my current using voltage equals current times resistance. So it's going to be my potential difference divided by my resistance, which is 120 divided by 4.81. I'm running out of space. 24.9. Don't forget the units. The units are very important. Some of you keep forgetting the units in every other step, or sometimes you don't write units at all, and I do need to see your units. Amperes, okay? Sorry about the messy numbers today. And that's how you combine. So this is as far as we're going. The next step is going to be to do tables and find the potential difference and the current in each of the individual resistors, which is going to be quite complex because we have circuits inside of circuits. So we're going to actually have quite a lot of tables. I'm going to be doing that. We're going to be doing that next week. Probably starting Friday and then on next week. Okay. Let me do an additional example so that we're ready to do some exercises in class today. So the examples in your book, let's do this one, which is quite more complex. Okay, so we're going to be doing some building up examples today. So this topic, it's very important that you build up. Okay. You're going to notice here how we're going to start working with easier examples, and then we're going to build up to the harder examples, which are actually up here. That's a harder example. That might be a little bit harder, and I have a few more that we can go through. Let's do this one right now, which is quite complex. So it's very important that you analyze the circuit before you start working, okay? I like analyzing the circuits as a closed circuit. That's easier to me. If you're having a hard time analyzing the circuit as one loop, you can break it down and open it at the battery and stretch it out until you draw this diagram. This also works for some of you. So you kind of cut it with a scissor at the battery and you stretch it out until you have a straight line. So that's going to be easier for you to see that you have. Focus. Okay. Okay, sorry about that. So you have pretty much, if they're in a straight line, it's in series. And whenever you have a break, you know it's going to be dealing with parallel. So right now I have parallel here, but the top two are not in parallel, they're in series. So I'm going to be combining those two first, okay? And then whatever I get from these two is going to be in parallel with the 4. When I'm done combining all 3 of those, the next step, I'm going to have 3 resistances in series. So it's really hard to see it all at once. It's easier to do it step by step, but it's sometimes good to plan ahead. So first, let's label my resistances. A, B, C, D, E, and F. Okay. So the innermost circuit I see here, the outermost circuit is the big loop. And then I have an inner circuit with the parallel in there. But the innermost circuit are these two that are in series. So I can easily combine C and D. So my equivalent resistance combining C and D, since they're in series, because they're in one loop, you notice that there's no break between them. You just add 6.0 plus 2.0. Always show me your work. 8.0 ohms. So once I combine two, I need to redraw the diagram. So let's go ahead and do that. So quickly, a quick sketch. I have my 9-volt battery. A, B. Sorry about that. Mine is going to be horrible, but yours should look better. Okay. So what I did is I still have my A over here. I'm just going to label them with letters. You can label them with letters and then put a key off to the side saying A equals B equals C equals, because I know sometimes it's too much writing to do in small spaces. Now on top, I combine these two into CD. So I can just call it CD because it's now 1. I have E, and I have F. So now I notice that CD, which is 8, is now parallel to E. So I can combine my equivalent of CD with E, and that's going to give me CDE. So 1 over CDE, because those two are in parallel, equals 1 over 8.0 plus 1 over 4.0. And that gives me 0.375. So RCDE equals 1 divided by 0.375, 2.67. Okay, so now I combined C, D, and E into one resistor. So if we were to shrink that down into 1, what do I have left? So you come and you draw it again. And it does help, and you do have to do this. Each time you combine, you need to draw and give me a new circuit. It's the only way you can do some of the most complex problems. So now let me do my next, which is going to be once again my 9-volt battery. And now I have A, B. I combine those three. Okay, and I have A, B. At the top, I have the combination of C, D, and E. And over here, I have F. So you notice at the very end, this is when you know you're almost done, when you only have one loop. And the equivalent resistance is just the sum of that loop. So A is 3.0. B is 6.0. C, D, and E together are 2.67 ohms. And F is 1.0. So my equivalent resistance is 12.67 ohms. Or 12.7 ohms, because we have one significant figure. Sorry, three significant figures. And if you notice, they have two significant figures. However, for these problems, I always want at least one decimal place. In the prior example, we used 2 decimal places because we did have one that was 2 decimal places long. So yeah, right now, always use at least 1 decimal place for all of your answers for all of your computations, whether it's resistance or current. And don't forget, once you're done finding your equivalent resistance, you can now find your current using the formula from chapter 17 that we've been using all along. V equals I times Req. Using a voltage of 9 volts, and your Req you just found here, so you divide to find your current. Okay, so that's, I would say, a medium difficulty level problem. So now we're going to be working in class to do additional problems together. So you have to have your paper and pencil ready, because I'm going to be calling you out so that you can help me work along. Everybody needs to be ready and working with me.